welcome to another Common Core geometry lesson by eMathInstruction. My name is Kirk Weiler, and today we'll be doing unit number 3, lesson number 8, confusingly titled AAS and Isosceles Triangles. Now, we've had a lot of acronyms in this course, SSS, CPCTC, SAS, things like that, and there's more to come. But today, we're going to learn about another way to prove that triangles are congruent, specifically the AAS method, and we're going to see how it links into some very important facts about isosceles triangles. So let's get right into it. All right, the angle-angle-side theorem. The angle-angle-side theorem. Let me read it over for you. If two triangles have two angles and a side of one triangle equal to two angles and a side of another triangle, then the two triangles are congruent. All right, now, this is very, very interesting because what we're saying now is that we don't necessarily have to have angle-side angle, i.e. the side between the two angles. What we simply need to have is a pair of angles equal to another pair of angles, and then one of the sides equal to the other. So for instance, take a look at this situation where we've got these two triangles, ABC and DEF. They've got two pairs of angles equal, 55, 55, 40, and 40. And then they've got a side that isn't between the two angles. And I'm claiming that this is now enough to prove that the two triangles are congruent. All right? So the first thing that we want to do in the first exercise we're going to get into is proving angle-angle-side. So let's go ahead and do so. All right. Exercise number 1. This exercise, again, is all about proving AAS. All right, so let's take a look. Exercise number 1. In the diagram below, AC is congruent to DF, angle B is congruent to angle E, and angle A is congruent to angle D. Letter A, and this is very, very important, why does this not, very critical, why does this not represent an ASA scenario? Pause the video right now and write something down if you can. All right, well, let's talk about it. Okay, the reason it does not represent an ASA scenario is because the congruent side pair does not lie between the two angles. All right? So the order of the letters in these kind of acronyms, ASA, matters, right? And we talked about ASA to begin with by saying that the side had to be between the two congruent angle pairs, okay? So in other words, if we were to use ASA here, we would have had to have known that this segment was congruent to this one, this congruent to that. All right, so this does not represent ASA. And yet, ASA is going to be key in proving that these two triangles are congruent. Let's go through the proof together, all right? And then we'll have you do other proof on your own this lesson. But let's take a look at this proof, okay? Letter B says, do a short proof that shows that given angle A is congruent to angle D, angle B is congruent to angle E, then angle C is congruent to angle F. So right now, all I'm trying to do is prove that these two angles, angle C and angle F, are congruent to one another. All right, simple enough. Measure of angle A plus measure of angle B plus measure of angle C equals 180. Measure of angle D plus measure of angle E plus measure of angle F equals 180. Why? Because the sum of any three angles of a triangle is always equal to 180 degrees, right? Once we've proven something in this course, we can use it. If you prove it, you can use it. If you haven't proven it, you shouldn't use it. So, we know this is true. But that means that we can say A plus B plus C equals D plus E plus F. Why can we do that? Well, that's the substitution property of equality, right? We can simply say, well, since they're both equal to 180, they have to be equal to each other. Some teachers might call this the transitive property of equality, and that would be completely okay as well. Some people might insist on calling it the transitive property of equality. I question whether it's needed. But I can obviously say the sum of the angles of this triangle is equal to the sum of the angles of this triangle. But remember what we knew. We knew that the measure of angle A was equal to the measure of D, and we knew the measure of B was equal to the measure of E, because that was given. We were told that. Ultimately, we're trying to prove that C and F are equal to each other. So what do? Well, we will just subtract A and D from sides and B and E from the two sides, and we're left with what we want. C is equal to F. Now again, this makes, or should make, all the sense in the world, right? If I simply knew what B and E were and what A and D were, right, then I could calculate what C and F were, and they would have to be equal, right? Because I would just add these two, subtract from 180, add these two, subtract from 180, and I would get these two angles, and they would be the same. So I'm going to actually mark these as now being equal because we just proved that they were equal. So letter C, now, why must the triangles be congruent? Why must these two triangles be congruent? Well, let's take a look at their diagram. I kind of moved it off. These two triangles must be congruent now by angle, side, angle, right? Because we have an angle equal to an angle, another angle equal to an angle, and the side in between them equal to each other. All right? So the two triangles must be congruent by angle, side, angle. So what's interesting about angle, angle, side is it essentially makes sense. If we know two of the angles of a triangle, then by default we know the third angle. Now you might say, well, why didn't we introduce this one way back when we were talking about side, 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 or angle, side, angle, or side, angle, side? Well, interestingly enough, back at that point, we hadn't yet proven that the sum of the three angles of a triangle was always a constant, was always equal to 180 degrees. The fact that it's equal to 180 degrees always isn't important. The important piece is that the sum is always the same. And so what that essentially lets you do is that when you have an angle, angle, side situation, it always essentially allows you to get the last angle. And because you then have the last angle, you now have an ASA situation. Now don't get me wrong, okay? You're not going to, when you have an angle, angle, side relationship, you're not going to have to prove angle, side, angle each time. You're now going to use the fact that anytime you have an angle, angle, side equal to an angle, angle, side, an angle, angle, side, then the two triangles are congruent because we just proved that. So we now have four ways of showing triangles are congruent: side, angle, side, 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 angle, side, angle, and angle, angle, side. Essentially, the only situation that you're never going to deal with is this one, side, side, angle. That will never be used to prove that two triangles are congruent. Side, side, angle, or angle, side, side, right, can never be used. And in pre-calculus, you'll actually explore a little bit of why that is when you take a look at what's called the law of sines, all right? But for now, we're not going to go there. What I need you to know and take from this exercise is that if you now have an angle, angle, side scenario, i.e. the side is not between the two, angles that you've proven congruent, then you can still use it to justify that the triangles are congruent. Let's get into some more examples. Okay, so now we're going to start using angle, angle, side. And let's look at the first proof that involves it. Exercise number 2. Given AC bisects angle DCB and angle B is congruent to angle D, prove that BC is congruent to DC. All right. Now, as always with a proof, if we can, we'd like to outline the proof and really try to understand how we're going to prove these two segments congruent, all right, before we ever put our pen down to the paper and start writing out statements and reasons. So let's start to outline what we're known, or what we're told. Mark up the givens. AC bisects angle DCB. Well, if AC bisects angle DCB, then what I know is I know that this angle and this angle are going to be congruent. I think I'm going to even give them numbers. I think I'm going to call them, I'm going to call them angle 1 and angle 2. Okay, so that's this given. I also know that angle B is congruent to angle D. All right, so I can already see that I've got an angle equal to an angle and another angle equal to another angle. Now, if it was angle side angle, ASA, I would now have to somehow know that BC and DC were the same length. But there's nothing about these two givens, and I've already used them both. There's nothing about those two givens that does that job. And yet, I do know that AC is a shared side between the triangle on the top, ABC, and the triangle on the bottom, ADC, right? So I have an angle equal to an angle equal to an angle, and a side equal to a side. So I'll be able to prove that this triangle is congruent to that triangle by angle, angle, side. How does that help me? Well, I'm trying to prove that BC is congruent to DC, right? I want to prove that BC is congruent to DC. So if I can prove that those two triangles are congruent, then what will I use as a line of reasoning to prove that those two sides are congruent? Hopefully, by now, you're looking for CP/CTC. You're looking for it, you're thinking about it. You're saying, oh, he's asking me to prove that two segments are congruent, so I'll probably have to prove two triangles are congruent and then use corresponding parts of congruent triangles are congruent, CP/CTC. So let's go through it. We actually have pretty much the whole proof, right? Step 1, AC bisects angle DAB, right? Because it's given. Step 2, angle 1 is congruent to angle 2. Notice that those two angles weren't marked on my diagram to begin with, but I marked them as angle 1 and angle 2 because it makes life easier, right? I can use the three-letter name. An angle bisector divides an angle into two congruent angles. Simple enough, right? Angle B is congruent to angle D. All right, another easy given there. Okay. And finally, AC is congruent to itself. Where am I? Where's my reflexive property? I lost it. Ah, there it is. The reflexive property. Okay? Now, all of that, right, is enough to establish that those two triangles are congruent to each other by the angle-angle-side theorem. All right? So triangle ACB is congruent to ACD by the angle-angle-side theorem. Now that I've got the two triangles congruent, I can say that BC is congruent to DC by CP/CTC. All right, after a while, it just sounds like random letters coming out of my mouth, okay? So let me pause for a moment, write down any steps you need to, and think about the logic of this proof. All right, let's keep going. Very easy proof with angle-angle-side. But now, we're going to talk more about isosceles triangles. Now, we extensively explored isosceles triangles back in Unit 2 by using rigid body motions and symmetry, okay? And we established a lot of different things. But now what we'd like to do is look at two amazingly important facts that involve isosceles triangles that we can then use in future proofs. Again, once we prove it, we can use it, okay? If you prove it, you can use it. So let's take a look at the first important fact. We will first prove that the base angles of an isosceles triangle are always congruent. Now, what are base angles? Okay. In most cases, when you have an isosceles triangle, it's drawn with its equal sides sort of being up here and its base, the non-equal side, if there even is one, being down here. The base angles would be these two angles. This angle up here is called the vertex angle, okay? But these two are the base angles. And essentially what we'd like to prove is that those two angles are congruent to each other. Specifically, though, even if the triangle isn't drawn this way, even if it's drawn in some other way, what we want to be able to say is if we know that two sides are equal on a triangle, then the angles that are opposite of those sides also have to be equal. Okay? So let me keep going. In the diagram below, isosceles triangle ABC has been drawn such that AB is congruent to AC. Let's mark that on our diagram right away. The angle bisector of angle BAC has been drawn and intersects BC at point D. All right, and what we want to do is prove that angle B and angle C are congruent to each other. So now, it's important because here the givens are kind of hidden a little bit in the text up here. And sometimes that'll be the case even on a standardized exam. You know, the givens will kind of get wrapped up in the text. So we really know two things to begin with. Number one, that these two sides are congruent, and number two, that this is the angle bisector. Now, we don't have to have the angle bisector, but since every angle has a unique bisector, it's okay to have that as the angle bisector. So how do we now prove that angle B is congruent to angle C? That sounds a lot like a CP-CTC scenario, right? We're trying to prove angles are congruent. What I'd like you to do is take a little bit of time and think about, given what we know about the diagram, how we could prove that B and C are congruent. All right, let's go through it. Well, first things first, let's get down the fact that AB is congruent to BC. And remember, that was a given, okay? Now, the second thing, though, that we were given is that AD bisects BAC. I keep losing my reasons here. But let's face the facts, that is also a given. I'm not sure where it went, but write it in. All right, so those two are our givens. Now, one thing that we can get immediately is the fact that angle 1 is congruent to angle 2. Why do we know that? Well, because an angle bisector divides an angle into two congruent angles. So actually, let me mark that on the diagram. This is congruent to that. All right, that's simple enough. Now let's think about this for a moment. Okay, I know this side's equal to that side. I know this angle is equal to that angle. If I can prove that this triangle here is congruent to this triangle here, right? You can see the two triangles. Then I'll know that the triangles are congruent and corresponding parts of the triangles will also have to be congruent. So far I have a side equal to a side and an angle equal to an angle. Do I see another angle equal to another angle? Another side equal to another side? Look for shared sides. So in this situation, what we know is we know that AD is congruent to itself. AD is congruent to AD. Why? That's the reflexive property. And that's now enough to conclude that this triangle is congruent to this one, not by angle, angle, side, not by angle, side, angle, but by side, angle, side, right? Whoops, I keep losing things. Let's write it down right here. Little gap there. Number 5, let's say that triangle ADB is congruent to triangle ADC. And is my reason there? Sure it is. The side angle side theorem, right? Those two triangles are congruent by side angle side. But I can now say that angle B, this thing, and actually let me turn it into red just to really emphasize that it's what we're trying to prove. I can now say angle B is congruent to angle C by CP-CTC. Get this out of the way so you can see it a little bit better. All right, so a bunch of things vanished on me there. It's okay, right? You know, big debate that I had in all these videos was whether I should write out all of this by hand or have it kind of nice and typed and just sort of magically appear. Unfortunately, when magic makes things appear, sometimes apparently things disappear. But regardless, understand both the structure of the proof and the extremely important result. The structure of the proof is simply that we've got an isosceles triangle, we bisect the vertex angle, we're now able to prove that these two triangles are congruent by side angle side, and therefore these two sets, this pair of angles must be congruent by CP/CTC. The structure of the proof isn't that hard, but again, the result of it is amazingly important. Anytime we have a triangle with two congruent sides, the angles opposite of those congruent sides must also be congruent. Okay? Let's see how that works out in another problem. Or in another proof. Let me put it up here, just so it doesn't get in the way. Now, again, remember what we just proved. A triangle with two congruent sides has opposite angles that are also congruent. We're now going to look at the converse of that, which is if we have two angles congruent, we're now going to prove that the sides opposite must also be congruent. All right, let's take a look at the problem. Using the same diagram as before, let's say we now have triangle ABC, but all we know is that angle B is congruent to angle C. Let me go back to blue and mark my givens, that angle B is congruent to angle C. And the angle bisector, BAC, is again drawn as AD. All right? So now we've got these two angles being congruent. This is still the angle bisector, which means 1 is going to be congruent to 2. Okay? So now, now we want to use this to prove that this triangle must be isosceles. And again, to kind of get a little bit ahead of myself, the general idea here now is that if we have some scenario where we've got a triangle that's got equal angles, then I'd like to be able to say that the sides opposite of those angles are also equal. Okay, and we're going to be able to do that through this proof. I love the fact that one of my reasons has already shown up. All right, and in fact, it's going to be the angle side theorem. I can't really make it vanish, unfortunately. Well, maybe I can, but not without losing everything else. So we're going to let it sit there. Now, why is it going to be angle side? Right? Well, just like in the last proof, we're going to want to prove that this triangle is congruent to that one. We already have the fact that the base angles are congruent. We already have that these two angles are congruent. The only other piece that we really have is the same one we had in the last proof, which is that shared side. AD is shared between those two triangles. So let's take a look at how the proof plays out, right? Angle B is congruent to angle C. Easy enough. It's given. AD, not coming up. Wow. All right, we're writing this guy out. AD bisects angle BAC. Also a given. Well, at least that side's working. Right? That tells me now, or it should tell me, that angle 1 is congruent to angle 2. Angle 1 is congruent to angle 2. Why? Because an angle bisector divides an angle into two congruent angles. Wordy, but the way it is. Again, if your teacher says that it's completely acceptable to put down the definition of an angle bisector there, thumbs up, okay? I may eventually even go that route just to have less written on the board, okay? Finally, and now it works again, AD is congruent to AD. We know the property there, that's the reflexive property. So at this point, I've got an angle equal to an angle, another angle equal to another angle, and a side equal to a side, but that side's not between the two angles that we know are those corresponding pairs, okay? But that's okay, because we can now say, I gotta wonder what's going on there, that triangle BAD is congruent to triangle CAD by that angle side theorem. Triangle BAD is congruent to triangle CAD by the angle side theorem. And now, right, we can say that this side AB must be equal to this side AC AB is congruent to AC because corresponding parts of congruent triangles are congruent. And finally, because we really haven't quite finished what we were supposed to do, and we're not going to get it that way, triangle ABC is isosceles. Why? Because the definition of an isosceles triangle. All right? Again, we could say, well, why is ABC isosceles? Because any triangle that has two congruent sides, at least two congruent sides, is isosceles. But here I think saying the definition of an isosceles triangle is perfectly acceptable. It fits that definition, right? Now again, there's the structure of the proof, which is important, especially because we're using angle, angle, side to prove a very important fact. But just as important as sort of the structure of the proof and practicing geometry proof is also the result itself. Again, that result being that if I have two congruent angles in a triangle, the sides opposite of those congruent angles are also the same length or congruent. All right? Where'd that go? Last problem. Okay? Many times you'll have to use one or the other, maybe sometimes even both, of those two things that we just proved in some kind of a problem. So let's take a look at this one. Exercise number 5. In the diagram below, BD is parallel to AC. AB is congruent to AC, and the measure of angle BAC is 78 degrees. Determine the measure of angle DBC. All right. Take a few minutes and see if you can find the measure of angle DBC. All right, let's go through it. Now, again, right up front, make sure you know what angle you're solving for. All right, so since I'm in red, I'm looking for the measure of angle DBC. I need this angle measured, okay? That's what I'm looking for. Okay, so what do I know? Well, I know that BD is parallel. Let me go back to blue. I know that BD is parallel to AC. And there's a ton that comes along with that, all right? And I know that AB is congruent to AC. Okay? Now we have to use both that parallel fact and the fact that AB is congruent to AC to figure out the answer. Let's first use this fact. Now what does that really tell me? It tells me that this triangle right here is isosceles. All right? With these two sides being the equal ones and the 78 degrees being up here. Now that means that we know that these two angles are equal. We can combine all of this with the fact that we have 180 degrees in a given circle to say, well, if I take 180 degrees and I subtract out the 78 degrees, I'm left with 102 degrees, right? Now that 102 degrees has to be split evenly between these two angles because they're equal to each other. So if I take 102 degrees and I divide by 2, I'll find that each one of those angles is 51 degrees. All right, let me write those into my picture. This one is a 51 degree angle, and that one is a 51 degree angle. Okay? That kind of uses up the fact that AB and AC are the same length. But now we can use some parallel line facts. What do we know? Well, marking in green, this angle and this angle, well, they aren't equal, this angle and this angle, because they're not corresponding angles created by parallel lines, they're not alternate interior angles, they're actually same side interior angles. And that means that this angle and this one, the two angles drawn in green, must add up to 180 degrees. Okay? Must add up to 180 degrees, right? Which means that we can do, actually I don't even have to do that much. No, I can even do it easier, sorry. Sometimes easier is better. Let me get rid of that little green angle marked. Sometimes I see an easier way to do it and I might as well just bail right now. The angle we're looking for is actually an alternate interior angle with the 51 degrees. With the 51 degrees, right? It's that angle made by a Z. All right? And because those are alternate interior angles, the angle that we're looking for must also be 51 degrees. See, I was going to go through a bunch of rigmarole, take 180, subtract off the 78, right? That would actually ironically leave us with the 102 degrees. Then I was going to take the 102, subtract off the 51, and I'd be left with 51, right? But I recognized as I was doing the problem that the angle I was looking for was an alternate interior angle with one that I already knew. And therefore, they must be the same size, 51 degrees. We did have to use, though, two important things. We had to use the fact that this was an isosceles triangle and therefore these two base angles were the same size. And we had to use the parallel line property that says alternate interior angles are congruent. Thankfully, though, I pulled out of the more difficult way of thinking about the problem before it was too late. All right. Anyway, let me step back, take a moment, look at this problem, and then we'll move on. Okay, let's wrap it up. So today we saw many different, very important things. Number one, we introduced a brand new way to prove that two triangles were congruent. That was the angle-angle-side theorem. And we'll see that pop up here and there in different proofs. We should be looking for it. So now we have four different ways: side, 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 angle, side, angle, side, angle, and angle, angle, side. And besides that, we also saw two extremely important facts that involve isosceles triangles. Number one, when an isosceles triangle exists, the angles that are opposite the equal sides must be equal in measure. And the converse of that, which is that if we have a triangle that has two equal angles, the sides opposite of those equal angles must be congruent or equal. So the triangle has to be isosceles. Equal angles in a triangle mean equal sides in a triangle. And equal sides in a triangle means equal angles in a triangle. The same cannot necessarily be said about other more complicated figures like quadrilaterals or pentagons or hexagons, etc. All right, we'll get into those in future lessons. For now, I'd like to thank you for joining me for another Common Core geometry lesson by eMathInstruction. My name is Kirk Weiler, and until next time, keep thinking and keep solving problems.